Here are the notes for Module 10. What I've done in this first slide is I've made like a reference sheet that gives us all in one place some facts that we know about different types of quadrilaterals, and also if that quadrilateral were to be placed on a coordinate plane, what are some formulas that can be used to prove that what you're looking at is that quadrilateral. So to start off with parallelograms, what do we know about the sides of a parallelogram? Well, we know that the opposite sides are parallel and that the opposite sides are congruent. So if you were to place a parallelogram on a coordinate plane, because the opposite sides are parallel, those opposite sides should have the same slope. Because those opposite sides are congruent, they should have the same distance. So you would use, slope formula and distance formula respectively. Some information about the angles. We know that opposite angles in a parallelogram are congruent. We know that consecutive angles are supplementary. For the diagonals of a parallelogram, they bisect each other. So if I were to put this on a coordinate plane, because they bisect each other, they should share the same midpoint. The point in the middle should be the same for both of them. A rhombus. A rhombus is just a parallelogram that has all four sides congruent. So if you look at what was placed here, it's basically identical to what we just went over with parallelogram, but now all four sides are congruent, which means all four sides should have the same distance. Also added, that doesn't apply to a parallelogram, is that the diagonals are perpendicular. They cross at 90 degrees, which that can be proven by slope formula. The two slopes would be the negative reciprocal of each other. And then just an extra, it doesn't really apply to the coordinate plane, but just another piece of information about the rhombus is that the diagonals bisect each angle. Each diagonal cuts the angles in half. A rectangle is just a parallelogram with all four angles congruent. So everything you see here is the same as you saw with parallelogram up at the top. Except for that, and also now that the diagonals become congruent. They don't just bisect each other, they're congruent. So if you had the diagonals of the rectangle, you can use distance formula to prove that they are the same. A square is a little bit of everything you've seen above. A square is a parallelogram. A square is a rectangle. A square is a rhombus. So every single rule, every property that you've seen above is listed here with a square. So a square, all four sides are the same, all four angles are the same, and in blue you can see if you needed to prove all the rules about the diagonals bisect each other, so they have the same midpoint. The diagonals are perpendicular. The diagonals are congruent. Every rule that you saw above applies to squares. Okay, now the first non-parallelogram, a kite. We know that on a kite, the consecutive sides are congruent. So if you figure out which are the two consecutive sides that should be the same, you can check out distance formula to prove that they're the same. We know that for the angles of a kite, the non-vertex angles are congruent. We have vertex angles and non-vertex angles, so the non-vertex ones are congruent. We know that the diagonal from that connects the vertex angles bisects the one that connects the non-vertex. It cuts it in half. So you can use midpoint if for some reason you needed to figure out where that diagonal was going to pass through. And we also know that the diagonals are perpendicular, just like with the rhombus. So we could use slope formula and check to see if the slopes of the diagonals are the negative reciprocal of each other. Finally, a trapezoid. A trapezoid, the bases are parallel, not both sets of opposite sides, but just the bases are parallel. So we could use check for same slope to prove if they're parallel. And if we have an isosceles trapezoid, the legs would be congruent. So you can use distance formula to check that out. We know that on a trapezoid, consecutive angles are supplementary. They add up to 180. And now that's if you go from one base to the other. And then finally, if you have an isosceles trapezoid, diagonals would be congruent. That would be the same thing as with a rectangle. You can use a distance formula. We also get into area a little bit in this module, so some formulas for area. All parallelograms, all right, the one thing they have in common is that their area can be found with base times height. But the rule is that the base and height have to be perpendicular to each other. So on a rectangle, since the sides are perpendicular to each other, base times height is just the length times the width. You just multiply the sides times each other. But on a regular parallelogram, where the sides are not perpendicular to each other, any one of the four sides can act as a base as long as you have a measurement that reaches that base at 90 degrees. It would have to meet that base at 90 degrees, and then you could just do base times height. Some other formulas for a trapezoid. Either one of these work. If you want to avoid the fraction, you can use the one off here to the right. But the formula for area of a trapezoid is the height of the trapezoid. Just like with a parallelogram, the height has to meet the bases at 90 degrees. Times the sum of the bases. You have to add the bases up and then divide by 2. This is, again, similar to a triangle. Because a triangle is just base times height over 2, but a trapezoid has 2 bases, so you have to add the bases. For a rhombus, since a rhombus is a parallelogram, you can use the standard formula for area of a parallelogram, but on most of the books that I've seen, you're not able to use that because they don't give you those measurements. So with a rhombus, we also have an option. You can use, this is actually the formula for a kite. Even though a rhombus is not a kite, because the diagonals meet at 90 degrees, you can just do diagonal 1 times diagonal 2 divided by 2. Because the diagonals are perpendicular, you can use that formula. And with a kite, you can do the same thing because a kite has perpendicular diagonals. And that's the only one we're going to use for a kite. Because the diagonals are perpendicular, you can do diagonal 1 times diagonal 2 and then divide by 2.